Hi everybody, this is Deva Chatterjee from Robin Systems, and today we are going to talk about how and why we should build an agile and elastic data pipeline. Data pipeline is becoming a very popular term these days, and most of you who have joined this webinar will probably have a good idea what a data pipeline is. But just to set the base for this presentation, I'll reiterate what a data pipeline is. It's an automated process that executes at regular interval to ingest, to clean, transform, and aggregate incoming feed of data to generate the output data set in a format that is suitable for downstream processing. So as you see in the picture, there is a input data set and it goes through a series of operations, and then that creates a suitable downstream processing for sort of consumers. Now, data pipelines have becoming very popular these days. As you can see in this chart, how it has grown in the last 5 years. This is taken from Google Trends, and we see that the trend is a lot of people are showing interest. But having said that, it's not that data pipelines are just a new thing that has been around for the last 5 years or so. There has been this concept was around for a very long time as well. The traditional data warehouses in effect were the early data pipelines of yesteryears. I mean, if you think about evolution of our data pipeline, we are talking about the data warehouse, the batch processing, getting data from an OLTP environment through the extract, transform, and load process into a data warehouse was the original data pipeline. It needed you to convert from third normal form of the data, from the relational form into, more often we would see star schema, where you will have a fact and dimension tables. And but the problem with that setup was that there was always a time lag between the data that you are actually analyzing on the warehouse and from the data that was actually in the OLTP system. Sometimes this time lag was days, sometimes it was weeks, and it was very expensive to run and maintain. A few years back, with the introduction of Hadoop, this process sort of was disrupted, and it from ETL, extract, transformation, and load, it sort of became ELT, extract, load, and then transform. And the modern day data pipeline basically has evolved from there on. And today, it sort of looks like this. There are 4 distinct stages where you have the data ingestion, where you are reading from different sources. You are taking the data and loading into our data storage more often. Sometimes even one of these stage may not exist. You store the data, then you transform the data using a data processing layer, and finally you put the data in a place where the final visualization can be done. So it is basically a 4-stage process: ingestion, storage, processing, and serving view. Now, keeping that in mind, today's data pipeline, there are several options for customers to build their own data pipeline using a bunch of different softwares available. Now, that actually makes this process very complicated. Now, as you can see on my left hand, there are multiple data sources. There's the databases which store the traditional transactional data, then there is social data, web data, sensor data, log data. Now, all this data, they feed into our data ingest platform. Usually it's Kafka or a Scoop or a Flume. And these, after they take the data, they actually put the data in a HDFS or a Cassandra or a H-based store, which then in its raw form is processed by usually Spark streaming, or somebody would run Cloudera, Impala, or even R on the stored data to actually to create the serving view for visualization. So for the serving view, we could put the data in Elasticsearch or a MySQL database or a Cassandra, or even provide REST APIs for the downstream visualization tools, which is essentially can be a Tableau or a Kibana or even something like Pentaho as well. So this is my slide screen just filled with bunch of logos. So it's not very easy when it comes to building your own data pipeline. For different use cases, different pipelines needs to be built. It can be, data ingest where you are doing through Kafka, Spark Streaming, and Cassandra. This is very popular these days. Recently, I worked with a big company where they are capturing some sensor data, and this is their architecture: Flume to HDFS to Spark to MySQL to Tableau. And depending on what you are doing, you have to build your pipeline accordingly. There is no set rule that if this is you have to use this bunch of softwares to build your pipeline. And there can be bunch of different use cases. Customer catalog or fraud detection. Internet of Things is very important these days. List management, messaging, all these different use cases can have a different setup of their pipeline. So, as you can see in the screen, I could only show only 3, but there can be numerous different permutations of these different softwares. Now, essentially, what you can think about it is that a data pipeline is a cluster of multiple clustered applications expected to work together in harmony. So, it is not just a single application that you spin up. It is a series of clustered applications that are tied together, stitched together, through which the data is flowing and is being consumed by end users. Now, when you, from a very operational point of view, when you look at this, you think as the operations guy or department, you think that there are several questions that crop up into your mind. How do you quickly deploy the entire pipeline? How do I handle spikes and growth? Because what if the ingest rate goes up? How would my pipeline react to it? When my data set grows, the workload grows, I want to avoid under provisioning. So I should be able to scale my data pipeline as soon as the workload grows. I should be able to set up multiple pipelines because you have multiple use cases, not just one for your data pipeline, without compromising performance on the same shared hardware. You don't want to procure hardware for each and every use case, and then you don't see utilization of those resources. You want to maximize your utilization and share the hardware for multiple pipelines. Then the other problem, which is mainly related to capacity planning, and as we are working with customers, we come across this quite frequently, that they really don't know how much hardware to allocate for your initial provisioning. A customer we just worked recently, they said, I want to have 100 nodes for my pipeline, but it will take 3 years for my data to get to that state. Do you want to invest upfront? What if your data doesn't grow and you have a bunch of underutilized resources? So these are things that you have to think. And also the other thing is that as the data pipeline matures, you want to extract more information, more value out of your data. So you would like to build analytics on top of it. So you want your developers to have access to that data as well. And those developers needs to sort of get access to production quality data, but they should not be making any changes to it. So there are many sort of considerations, challenges that you have with your data pipeline setup. Now, if we say that when you talk about these challenges, these are not challenges just for the one application of the pipeline. The pipeline consists of many such applications. So the challenges grow based on the complexity of your pipeline. The more the components in your pipeline, the more difficult it is to handle. Now, let's say we say we will solve your problem. So you have a requirement to quickly deploy your entire pipeline. You say, yes, we can do it. But then your question should be, will I be able to use my existing hardware to set up my pipeline? Like I said, avoid over provisioning and under provisioning of hardware. So your concern is that I need to have just enough hardware so that I don't waste resources. When I said that you need to share data with your developers, and your concern would be, how can I make sure the developer has access, but we are preventing them from making any changes? So it's a security thing as well. And the most important, I think, for any pipeline is, how do I handle seasonal spikes? We are working with a retailer who's, large retailer. During their Christmas time, they want to, beef up their recommendation engine, their recommendation pipeline, and they want to add compute resources during that time. But as the Christmas time is done, they want to take those compute resources out and bring back the data pipeline to their normal state. So the question is, even if I allow you to scale, will your platform allow you to scale each of your data pipeline component independently of each other? And then finally, in order to reduce your CapEx, you want to run your data pipeline on a shared infrastructure. But the concern I hear from most of our customers is that, how will I be able to address noisy neighbor situation? I'm willing to share my hardware with my other applications, but I don't want one application inadvertently impacting the performance of my current application. So, this is sort of the checklist. Now, what I'll do is I'll talk about each of these problems separately, and how Robin helps you to address these problems, and how you can sort of get going and address those problems when you're setting up your pipeline on Robin's application virtualization platform. So to begin with, I'll just give you a very high-level overview of how Robin works. Robin is basically is a software-only solution that runs on commodity hardware, and it consists of two separate layers: the application-defined compute plane and an application-defined storage plane. So basically, what happens is that we carved out a scale-out. We have created the scale-out block storage layer that actually essentially captures all your data, and every data-intensive application are deployed as Docker or LXC containers. So essentially, you are going to create, when you spin up a cluster, you create your cluster components in separate containers running on top of commodity hardware, where the storage is actually carved out of all these from your storage plane, and they are mounted as block storage in all of these containers. I said, it's mouthful, but you'll probably get it as I talk about it in the subsequent slides. So, and then we have built in a bunch of application lifecycle management functions that help you to deploy, to scale, to failover, to snapshot, and to clone and ensure quality of service for your application. But the whole premise of our platform is that you deal with applications and not virtual machines or containers. It is completely abstracted out of the end user. We have the complexity, we deal with the complexity, Robin deals with the complexity, and the end users deal with the application. They interact with the application without actually knowing that the application is running on top of containers. So having said that, I'll dive into a little bit more details. How do we create this application-aware architecture? We have what we call an application manifest, where we define the anatomy, how the application is structured. So you think about in your data pipeline, you have several components. Each component needs to be defined, and where in this file we say that, hey, Kafka is talking to Spark, which is in turn talking to Cassandra. It looks like this. You have to give it a name, a description, and whether you want to support operations like snapshot and clone, then where you have different roles. this manifest is specifically for Cassandra. Cassandra, when we set up, we have different roles like seed and member, and then we say whether you want to use a Docker image or an LXC, because both are containers, and it depends on the customer's choice whether they want to use a Docker or an LXC container. And what are the resource requirements? This is very important, because when you are creating an application, when you're using creating a container, this container will have many different volumes. One volume can be carved out of an SSD disk, while some other volumes can be carved out of an HDD. And then you want to also specify what would be the amount, number of CPU you want to allocate, what would be the amount of memory that you want to allocate to each of these roles in this particular application or cluster component. Now, you could also define a particular cluster, whether it wants to be multi-node or not. So when you say, I want to create a Cassandra cluster, I want one seed node, but I want maybe 4 member nodes. So you can define that as well. In the next part, you define the configuration parameters, where you can provide a name for the cluster, and then these are hooks that you define in the manifest that would be executed after every action that you take on the Robin platform. We also have ways to actually help you define affinity and anti-affinity rules, so that it actually lets you specify whether 2 containers are, let's say 2 member nodes of a Cassandra cluster are not running on the same physical host. They will be spread across 2 hosts. Think about, let's say you have a pipeline where you are using Logstash, Elasticsearch, and Kibana. You want the Logstash nodes not to be running on the same host, or maybe you don't want the Elasticsearch nodes to be spread out in multiple hosts. And I'll show you how we do that for Elasticsearch and other applications as well, because I have a few demos as well. So with that said, what we do is, we get into the heart of our data pipeline these days, which is usually Hadoop and HDFS. The challenge, I've seen a lot of articles in the internet which says, can I build my entire pipeline using Apache products, open source products? So it is possible, but there are a lot of challenges as well, because when you talk about Hadoop, it's not a single product. It's an ecosystem of products. So, there are several components that needs to work together if you want to build your data pipeline using just Apache products. So these are all these components that came out in Hortonworks 2.3, and it's a bit dated, but this is all the versions. And so any change in the version becomes a sort of a nightmare for the operations to keep up to speed with the changes in each of these components. And provisioning of enterprise Hadoop takes days, weeks. It's a very arduous task. So what we do, we define the Hadoop configuration in the manifest that I showed in the previous slide, and we allow you to create an entire structure for your Hadoop ecosystem, now Hadoop cluster. Now, we will create a pre-baked image for all the components, and then take each of these different components and put it together in one single Robin container image. That can be a Docker image or an LXC. And we provide this image is nothing but a zip archive. It's basically a tarball that is available to you, and you use our UI to actually use zip tarball to lay out your cluster. And the thing is that the notion that we use is that you build once and deploy on demand as many times as you want. So you can use the same configuration to deploy over and over again. And also, even though you are using the image, you could actually build and configure your cluster in different ways. So in one cluster, you can have 10 data nodes, while in another one, you can have 5, but you are using the same image. It's a runtime configuration that you are altering to lay out your Hadoop cluster. So with that said, I will actually show you how quickly we can provision a Cloudera cluster here, and I'll This is, I'll open up a recorded demonstration. So here, this is our UI, and here is our dashboard, where I will go to the nodes, basically to show you that this is a 8-node Robin cluster. They are very beefy machines. Some are convert, some are compute only. We can also see this in the UI, that amount of SSD and HDDs and memory that we have. And these are actually split into 3 separate racks. Racks are basically, sort of segregate this. So in rack 1, I have 3 nodes. In rack 2, I have 3, and in rack 3, I have 2 nodes as well. So total 8 nodes segregated in 3 separate racks. So now let me go to the application bundles page that I had discussed earlier, and here I'll pick up the Cloudera bundle and provide a name for the cluster. And the rest, here we show you how you can change the CPU, the memory settings. We allow you to provide Docker, options, runtime, that you can use. You can specify number of data nodes. This is the gateway node. You can increase the number of gateway nodes or the, for the other roles as well. So we have Hive, we have the name node. We have name node HA as well, which is required. Uzi and resource manager followed by Spark. So it's a very complicated cluster. And then we have a zookeeper where we have also specified 3 nodes. So what we want the entire cluster to be spread out across those 8 nodes. So we also allow you to specify, copy this template and use it at other times. And here we show you how you can define affinity rules so that you can make sure that your zookeeper nodes are not running on the same rack. They're spread across 3 racks. So now I click on provision application, and that kickstarts a job on the Robin job scheduler. It uses the Robin jobs framework, and it kicks off the job, and it will run for some time. And since this is a recorded demonstration, won't bore you with that, but we can track the job on the back end on our command line as well. For somebody who wants to track jobs, we have the Robin job info command that lets the administrator see at what stage these jobs are, and then you can come back, and the application is provisioned in like 10 minutes and 13 seconds. So you have your Cloudera cluster ready in 10 minutes, and you can see if there are 15 such containers spun up based on the request, based on the configuration that I suggested. And you can see each data node has been provisioned in a separate physical node and separate racks. Zookeeper as well gone into separate racks. And this is the setup. And we can also, just like you do, this is the familiar Cloudera manager screen, which is accessible to the administrator as if there is no change to the application. It is exactly the same, and you could log into each host and look at the different Docker containers that we have provisioned as part of this cluster install. So the whole point of this demo was that how simple it is for you to provision a particular cluster on the Robin platform. And I'll show you another one. It's not just Cloudera or not just Hortonworks. It works for other components of your data pipeline as well. So with that done, I'll move into the other questions. Remember, we have like 6 questions that we started with. And the other most important question that we have is, and I think this is very important, how do you handle seasonal spikes and growth? Your data can grow at a different rate than your CPU requirements, or there can be just spikes that happen once in a year or twice in a year. How do you address those spikes? Now, in Robin, what we can do, we allow you to do both scale up and scale out. So sometimes scale out is not just a solution. What if you remember, we are using containers to provision your application. So containers are running on a physical host, and when containers are provisioned, they are assigned a certain number of CPU cores and a certain memory and read and write IOPS, which can be specified on Robin as well. So Robin actually allows you to do on-demand scale-up that actually, removes the requirement of data redistribution. You don't need to stop the cluster, and it is the best way to meet temporary or seasonal demand. So what all you need to do is you basically change your CPU cores from 2 to 4, and then your containers have more CPU to use for sort of compute processing. But that may not be enough as well. So you may actually want to have more, let's say, read IOPS, read bandwidth. So all you do is come to read IOPS and slide the read IOPS slider, and you have more read IOPS bandwidth to your cluster. Now, sometimes it is, you run out of storage and you have to do scale up because you want to add another node, another more processing power on another particular physical node maybe. So what Robin does, so let's say this is my setup where I have a 3-node Cassandra cluster, and I really want to add a node and right size my cluster because I know there is growing demand. So all you do on the scale out screen, scale out member screen, you go and just hit on scale out. What it does, it will add an extra node, and it will rebalance the data, and then it will become part of the cluster automatically. So the existing application doesn't suffer any outage or any changes. You can just add an additional node just by pressing, with a single click of a button, you have now new members or new nodes to your cluster. So the other question that we asked before was, how can I provide developers access to data? So this is usually a very, the common answer is that you should clone the data. Why can't I clone the data and give it a copy to the developer? Now, problem is, if your data source is hundreds of terabytes, do you want to clone and provide 100 terabytes to your data? Now, what Robin does, Robin actually allows you to create thin clones of your existing data, and then it makes sure that the IOs from the cloned environment doesn't impact the IOPS from your production environment. So essentially, we are not copying the entire data. We copy some metadata about the data and spin up our development environment for your developers to access. Now, sometimes I've been visiting meetups and meeting customers as well. So why do I need to clone my pipeline? You don't really need to clone your entire pipeline, but parts of your pipeline. Let's say and this is one of the customers that we are working, your serving layer is basically a MySQL database, on top of which the Tableau connects and generates its report. You want your developers to get a copy of that MySQL environment and work in parallel, work on development in parallel, and when your production system is in. They have access to production data, they can work on it. And so the requirement is not to just clone the entire pipeline in a single click of a button, but to clone some parts of the pipeline as required. And there are many requirements, use cases for which you would really want your pipeline to be cloned. The ad hoc analytics, test upgrades, DevOps is another use case. Testing changes. We were working with an Elasticsearch customer where they're saying that, I want to reindex my field, our date field, our text field needs to be converted to a date field, and then it needs reindexing. I want to make sure how long the reindexing takes before I put that change into production. Yes, we said, we can clone your environment. You do the reindexing change, test it on this cloned environment first, and then move to your production environment. And of course, integration testing is another reason why you would need a cloned environment. You can do the integration testing. What if you are introducing a new component to your pipeline? You can do that as well through integration testing in a cloned environment. So, what Robin allows is basically for an existing cluster, we simply take a snapshot. This snapshot actually allows you to, as a reference point, to make a point-in-time copy of your cloned environment. So, you take a snapshot, and then with a single click of a button, a similar-looking clone cluster will be spun up in just few minutes. So, I would rather show this to you instead of telling that it works in Robin. How about a demo? So, like last time, I'll try and see if this works. Okay, and here is my demonstration. I will actually start with logging into our Robin UI, and I'll show you actually how the provisioning works here. I'll go to my applications bundles page. By now, you have seen how I did the Cloudera cluster, but this time I'm going to provision an ELK cluster. So Elasticsearch has two roles, the Elasticsearch master and the Elasticsearch slave. Look, they are all Docker-based containers, and then there's Logstash and Kibana as well. Each of these components can have multiple nodes or multiple containers. So, and you can specify the CPU, the memory of each of these components, how many volumes, whether it's hard disks or SSDs, environment variables through which the different components of this ELK pipeline talk to each other. So you specify a name of an app, and for this one, we will have 3-node Elasticsearch and a single node Logstash and 1-node Kibana. So when we click on provisioning, it, as I said, it just will spin up a bunch of jobs, and it actually happens in 49 seconds. You saw that. And when the ELK app is running, I can go to this URL, and you can see there are 3 nodes as we have configured during installation. And now what we will do, we will log into one of the nodes, Logstash nodes, actually the physical node which is running the Logstash, and configure some data capture. So we provide the name of the Elasticsearch, IP of the Elasticsearch host, and then copy a FileBeat configuration file in the Logstash. Then we can see verified Docker logs whether the configuration has taken effect or not. And immediately what we will see is that we also need to make a change to FileBeat because it has to know where the Logstash container is running. We'll make that change and restart the FileBeat process. Now let's go to the Elasticsearch URL, and you can see that we have added an index for capturing information from Robin logs. So we are all log entries in Robin logs are now being indexed. So now what we will do is we will actually create a snapshot for this application. So what is a snapshot? As I explained, it's a point in time image of the entire data and the configuration of the application. So we create a snapshot just to make sure that this is where the initial state of the cluster is. So once we'll reuse the snapshot in the subsequent part of the demonstration. So here, now we will scale out Logstash. It's very simple because I want to create another feed into Elasticsearch. So scale up takes 4 seconds, and we have a new container. We'll log into this host and set up a new ingest from Twitter. So we will see that new container has been spun up. You can see the status is just about a minute because it just spun up. And what we will do, we'll create a Logstash Twitter configuration file, and we will specify the Elasticsearch IP address here, on that particular configuration, and then copy this configuration into the Logstash container that just we spun up, a few minutes back. So, and we can see that the configuration change has taken effect as well. So with that, what we can do, we can come to the indices, and we can see that there is a now Twitter index that we just created. And now if you look at the right hand side, the number of documents index is actually increasing from 1176 to 1268 and now 1352. Slowly it is increasing, so it is working now. So we have, so what in the last few minutes what we have done, we have created an Elasticsearch, L cluster, Logstash, Elasticsearch, and Kibana. We created two, sort of feeds, data ingest, where we created one for the logs that we have on our platform, and another one to sort of capture Twitter for specific keywords. And then we created a snapshot. Subsequently, we have added a node to our Logstash component. So it's had one to begin with. Now we have two nodes. So now what we will have a requirement, let's say we want to create a clone of this Elasticsearch cluster as of the point when we took the snapshot. So remember, we did not have the Twitter index at that snapshot, so we want to create a clone as of that point. So what we need to do, we will go to our snapshots page and use that snapshot to say, give me a thin clone, and name it clone, and click on apply, and you will see that it actually happens in very quick time. In about 35 seconds, we have a cloned cluster of Elasticsearch up and running, and it is online as well. So if you recall, we can go to our Elasticsearch URL, and if we query for the indexes, well, this is the number of nodes, so it has got 3 Elasticsearch nodes like the source cluster. And if you query for the indexes, we see only 2 instead of 3, because if you recall, we had taken the snapshot when it had 2 index. And so it basically, the platform allows you to take point-in-time snapshots, which can be either used for clones, or if the application has any problem, like you have an upgrade issue, or you have data corruption issue, you could use the snapshot to roll it back to a point in time where you knew the application was in a working state. So with that, what I will do, I'll move back to my slides. Well, I'll finish this, and so now let's take a snapshot of the cloned environment as well. So we create a snapshot, and so the snapshot of the snapshot, and then what we can do, this is the other use case that I was talking about, that what if something happens to your data. So I'll use a curl command to actually delete one of the indexes. So I have data corruption now, and the index is no longer available. You can see the other index is gone. So what I will do, I'll come back to this snapshot, and now I'll say restore to this point, because I took the snapshot when there were 2 indexes, and one index was deleted by, let's say, by accident. And this snapshot runs, this time travel or the restore runs for a while, and the containers are still provisioned with the same IP addresses. They are restored with the same IP addresses, and magically you see that the previous index that I deleted is back and is available. So this is, in the meantime, on the source one, you can still see Robin, Twitter, and Twitter is merrily indexing documents now. It went from 1300 to 33,000, and this was, in a nutshell, our demo. So let me go back to my slides. Now the interesting question, let's discuss how we can address or avoid under and over provisioning. Now this is a capacity planning problem, and a lot of these capacity planning concerns come from the fact that you are concerned about performance predictability. You don't want to run multiple applications on the same hardware, because you don't want one application to impact the other one. So this is sort of an scenario where we see currently, we see each of their data pipelines, or each component of their data pipeline run on dedicated set of hardware. They are not sharing the resources, as a result of which you have hardware sprawl, you have a bunch of machines, but underutilized or not fully utilized. And, all results in high OpEx as well, because you have need people to manage these machines, patch these machines, make sure that they are all working together. So with the Robin containerization platform, what happens is that you can create a unified pool of resources by pulling all these components. This is something I have spoken earlier as well. And then using the same hardware, you can spin up your applications inside containers. Docker, LXC, they can be spun up using containers on the same set of hardware. And the users, they access this application or their existing components of the pipeline using as if nothing has changed. And what happens is that after you do this consolidation, you actually see there is a lot of available capacity still on this, on your existing pool of resources. So what you do, you actually spin up more services and bring up new, customers or new applications over on the same set of hardware. So you not only consolidate your application, but also make sure that the extra capacity that becomes available from your hardware is used to spin up other components of a pipeline or a separate pipeline itself. So this is very important. And how basically it works? We help you to share the peaks and troughs of these unconsolidated application, so that you require, we increase the utilization of your hardware, but when we consolidate these applications, they increase the utilization, but you have more space, more resources to run other applications as well. Now, we can consolidate, it's great, but how about how do we ensure that we can run multiple clusters on the same setup, but there is no performance compromise? This is a very important aspect when you are talking about data applications itself. This is where, this is usually the deterrent why customers don't run multiple applications on the same, infrastructure. Now, what Robin does, as I said, is a very application-centric view to everything. Robin allows you to do max IOPS to throttle usage, so basically addressing the noisy neighbor problem. We do min IOPS to guarantee performance. So basically, when you define an SLAs, we actually, you say that, I'll do this response time, but this response time will need a minimum 20,000 IOPS. We actually allow you to do that. And then we allow you to prioritize relative weights of applications. So you can say application X will have more priority over application Y. So even though, these priorities can be time bound, between a certain time of the day, you want to provide more priority more priority to one apps over the other, or one component of the data pipeline over another component. They are basically sharing the same hardware, but one component, let's say your Elasticsearch component has more IOPS priority than your Kafka. I mean, this is how, because your Elasticsearch has to write the data on the disk. Kafka may not need to write all the data. It is a streaming application. So we allow you to enforce, as I said, max on the containers, the min on the storage side, and priorities are also ensured on the Robin storage, the container data layer, and that's how Robin controls the entire I/O pipeline. We can truly enforce QoS. Not, a lot of hardware providers say they can provide quality of service, but they do not. Once you have to do a lot of scrambling and basically find out, okay, which volume maps to which application and then turn QoS on. But with Robin, it's really because we have the entire visibility from the application to the disk. So we help you to set QoS at each layer of your application. Now, this is a problem for the Hadoop system. Usually applications have multiple data volumes, and this is very common for all data application. Now, without Robin, you have to create IOPS for every volume that you attach to a container. But in Robin, we actually work on the application itself and allow you to throttle max IOPS per app. And you don't have to go in and change each volume one at a time. This is possible because we control all IOs originating on the compute host because it's coming on from the container that we have spun up. And we do IO tagging and application-aware IO scheduling. So these are the two reasons why we can control IOPS at a application level and not on an individual volume level. So let's walk the walk and talk that. For some reason, I will open my short demonstration here. A very quick demonstration, the Cloudera cluster that I provisioned in the earlier demonstration. Let me go to the gateway node and log into the console. And here I will start a YCSB workload. It's like 800 million records are being read from this from this Cloudera cluster. Now, when we go to the actual host where this container is running, we can verify what is the volume of what IOPS are being hitting the disk. And so you can see here that the the pink one, there's a pink application which is coming on the way of the red gateway applications. We can go to the pink application and basically throttle it down from 60,000 to 5,000 IOPS. And now when we go back to the host, you will see that really it is now down to 5,000 and rest of the IO bandwidth is available to the gateway or my Cloudera cluster. So this is that simple. And this is so simple that we can do it through our REST API, and you can see how it has improved the operations on the Cloudera side. So this is a very short demo of our this feature, and let me go back to my presentation. So sort of summarizing what we started with, will you be able to use any existing commodity hardware for your data pipeline? With Robin, you can, because we are a software-only solution that is installed on the existing commodity hardware. Will you be able to just have enough resources? Yes, you can, because you can scale up and scale out. We make sure by consolidation that you have enough resources to run all your application. How can you prevent developers from making changes? Because we give you snapshots and we allow you to clone your application and spin up a separate cluster which the developer is accessing. So your production data is always safe, and they are not going to they cannot make changes to your production data. Can you scale out each component of the cluster? Yes, we showed you how I could scale out only the Logstash component, added more nodes to it, and the cluster could process a new Twitter index using on the same setup itself. You don't have to add a new physical node to set up that processing. And lastly, we showed you how you can address the noisy neighbor problem with our simple QoS solution that is built on top of each application. It's out of the box. You don't have to do anything. And the best thing is that the application runs as is whenever you are making changes. No need to take an outage or change bring down certain services and bring up. As long as the application can dynamically adjust to the new resources, we provide you with these switches that you can use to make your all the components of your pipeline, or rather I would say the entire pipeline, to be very elastic and agile. Before I sort of finish my presentation, I wanted to say, what are the sort of the benefits and value props of our platform. We provide cluster consolidation with predictable performance. We help you to eliminate cluster sprawl. We create an elastic infrastructure that leverages dynamic quality of service controls for each resources, CPU, memory, and network and storage. We enable multi-tenancy with performance isolation and dynamic performance controls. We help you with agile provisioning. You can deploy multifunctional data pipeline components with a single click of a button. We can scale out and scale up instantaneously to meet application performance needs. We help enable data sharing, as we showed you how to using thin clones of the entire cluster. And finally, we allow you to do time travel, restore or refresh your cluster to any point in time. Even my Elasticsearch cluster had a data corruption. We could actually bring it back to the original state with a click of a button. And so these values or these benefits actually lead to several high-level business benefits. So we help you to maximize your data center utilization. That sort of helps you to guarantee predictable performance. Agile provisioning helps you to do faster time to market, one-click lifecycle management, and it sort of makes your barrier to create, or removes the barrier to create your data pipeline. It doesn't take days or weeks to set up your pipeline. Just a click of a button away for you. And we simplify operational support. So with that, I will say thank you for listening to this webinar. I have few more minutes. What I will say is that if you have any questions, we can take those questions. I'm looking at the screen. I have a question here. It says, how many, is it possible to run set up a data pipeline or using Docker? I mean, I addressed that question in the presentation itself. We do support Docker-based clusters, and we also have support for LXC. So it's your choice how you would like to set up your data or components of your data pipeline. Now, the other question that we have is, can I scale across my on-prem and AWS or any other cloud vendor? So I would rephrase that question from saying that, do I have hybrid capability? So we are currently, our solution is on-premises only, but we are working on creating a solution that will be able to span across your data center onto the cloud. So think about it that you have a data pipeline created or component of a data pipeline on your own data center, and you want to, for a seasonal demand, you want to spin up few compute resources in the cloud so that you can run your reporting or some other analytics processing in the cloud. You could do that with Robin, and then after the demand is, or after you have done your application work, you could actually destroy those cloud VMs and be entirely back, sort of scale back to your data on-premises setup. So we will support cloud bursting and scale back as well. That's on our that we are currently working on actively. So I don't see any other question. I would thank you for everybody for listening to this webinar, and hopefully you will find value, and please reach out to us. We are at info@robinsystems.com. You can reach out to me as well. My email address is deba@robinsystems.com if you have any further questions on this webinar. Thank you for listening.